When I have a spring that is hung from the ceiling at its original length and add a mass to it, the spring is going to stretch until the force of the spring is equal to the force of gravity. The object will then remain at rest, assuming that I lowered the mass slowly. So if I was to have my hand underneath this mass and attach it to the spring, and then slowly lower my hand, open palmed, the mass would stretch the spring out, increasing the force of the spring until the point where the two are equal. And then as I lower my hand some more, the mass would pretty much just stay at that location with very little or no movement. However, if I was just to hook this mass up to the spring and let go, the mass would stretch the string downward to the point of equilibrium, but because of inertia, the mass would then continue to fall a bit, and then it would be pulled back up because there'll be more force of the spring upward than gravity is going down, and the object will then start to move up and oscillate up and down for quite some time until air resistance causes the spring to stop moving. So we're going to oversimplify things and just simply say I'm attaching this mass to the spring, and I'm slowly allowing the mass to stretch the spring out to the point of equilibrium. Once it's at that point of equilibrium, the force of the spring upwards and the force of gravity are equal in magnitude. Please notice I have a downward displacement, which means it's negative. My force is pulling in the upward direction, and a negative k times a negative displacement is in fact a positive force. So vectorially, everything is making sense, which is a very good thing because the only way I can counteract the effects of a downward force of gravity is by an upwards force of something else. In this case, it's a spring. If we apply Newton's second law, we can easily see that the force of the spring is equal in magnitude and opposite direction of the force of gravity, as we can see from our diagram. This means k times delta x1, because that's the first distance this thing has been stretched, must equal the force of gravity. This is a very important concept that we're going to be applying very soon. Another equally important concept right now is that the net force of this system, since I'm in equilibrium, is in fact 0 newtons. So we can actually call this line right here the line of equilibrium. This is not an official physics term, it's a term that I use, but it just really identifies this as the point on where the system is in equilibrium. It doesn't have to be at rest. Once before, if we were to just simply drop the mass, it would have fallen past the line of equilibrium and it would oscillate back and forth. But it would be trying to get to this line. This is, if you will, the system's quote-unquote happy place. It's where the mass wants to be right now because it is the balance point between the two forces trying to pull on it. Now, if I take that very same mass and I stretch it further beyond equilibrium to another length, so I stretch an additional delta x, which we'll call delta x2, meaning the full displacement of the spring is actually delta x1 plus delta x2, I would be out of equilibrium, and I can now have an acceleration. Now, this looks like it could be very involved because I'll have multiple forces in the situation. They're going to be out of sync with one another. It's going to be off balance. We have multiple delta x's that need to be added up, but there's actually a huge simplification that we're going to see in just a few moments. Since the force of the spring must equal negative k times delta displacement x1 plus delta displacement x2, the summation of the two distances that stretch the spring individually. The net force must be the total upward force plus the downward force. So we have the force of the spring plus the force of gravity. But the force of the spring, like we said, is k delta x1 plus delta x2, the summation of those two things. I can distribute my k value to both of those. So I actually see that it's equal to the force of the spring for the original displacement, whatever that was, plus the additional force that would be generated for the additional stretching. Those are my total forces up, plus my force of gravity going down, must equal the mass times acceleration of the system. But k delta x1 was actually equal to the force of gravity. We know that. That's at the point of equilibrium with just gravity. This means I can replace k delta x1 with negative force gravity. Negative because it's going against the force of gravity. It's pulling up while gravity's pulling down. So my equation now comes out to be negative force gravity, replacing k delta x1, plus negative k delta x2 plus the force of gravity equals ma. Well, I've got the force of gravity on the same side of the equation. One is positive, one is negative. This means they cancel out. And the net force on the system is actually equal to the spring constant times the distance the block has been stretched from equilibrium, from its happy point. This is a shortcut method to finding the net force on a block that is hung from a spring that has been stretched from the equilibrium position of the system. Not the original length, but the equilibrium position. Please notice, when I didn't stretch the block from the equilibrium position, the net force was 0. And I have no displacement from the equilibrium line. Here, my delta x2 is equal to 0 meters, which relates to 0 force. In this case, we're going to now take the mass. Instead of lowering it, we're going to actually raise it up, compressing the spring, making it shorter than the original length that it was before. In this case, delta x2 is going to go against delta x1. But even though this is now compressing the spring, we still have the same kind of effect as we did before. The force of the spring at its new location is still going to equal negative spring constant times the summation of delta x1 plus delta x2. The only difference here is they're opposite signs, so delta x1 could be a positive, delta x2 then would be a negative. Or delta x1 could be a negative, and delta x2 could be a positive. Either way, this would be reducing the total sum magnitude of the two displacements. My force, or as I say, my spring constant, still distributes through, and I still come up with negative k delta x1 plus negative k delta x2 plus the force of gravity equals ma. I can still break the force of the spring at its new location into two sub-forces. One force being the original force of the spring pulled from its original length, and then the second force, the additional force of the spring being pulled away from that equilibrium position. Again, k delta x1 is equal to force gravity's magnitude, so negative k delta x1 is the negative force of gravity. The force of gravity cancel out, and my net force is still equal to negative k delta x2 equals ma. Again, delta x2 is the distance pulled from equilibrium. That's all this really here is. This is from equilibrium. And just like before, if I had not pulled any additional distance, this would be 0, and my acceleration would be 0. It's very important to stress that we are not saying here that the force on the block is equal to K delta X2. Only the overall net force between the force of gravity and the spring force itself are combined up to the net force is equal to K delta X2. So there are going to be many cases in where we will have an object that is hanging from a spring oscillating up and down in the vertical direction. When that happens, we often see a lot of people simplify the forces down from being measured from the equilibrium position instead of the original length of the spring. If we are measuring from the equilibrium position, that means that is our origin, that is our reference. All measurements for displacements are being measured from that. We can simplify the net force to just being K delta X from equilibrium. This was our delta X2. There was a delta X1 somewhere along the way over here, but the force of gravity had nullified that out. So any imbalance that we see is only going to be from K delta X from this equilibrium position. So this is a nice shortcut. This, however, only can be used when I am oscillating up and down, and the only two forces acting on the object is the force of gravity and the force of the spring. Any other condition applying to this, any third force, this not being hung vertically, anything that deviates from this, this will not work. So this is only for hanging system with only two forces, and those two forces being gravity itself and the force of the spring. Any other system, and I have to go back to my free body diagram, measuring everything from the original length of the spring and just solving it that way.